Yiluo, LiTenn.
All right, let me share my screen. Share. My sharing, correct. Can you see my slides?
Yes.
Okay. See me now? Working?
Yes, it's good.
All right. Hello, everyone. My name is Nadie, Yiluo, LiTenn, and today I'll be presenting about black hole entropy, holography, then and now with random tensor network. So let us start with a little bit of introduction and motivation. Our big goal is to ultimately understand quantum clock gravity, and an important and promising tool for that is holographic duality, which is a duality of the bulk and the boundary. In the bulk, we have a theory with gravity, and on the boundary, we have a theory without gravity. So for example, quantum field theory. So imagine if you have a state in the bulk, it will have a dual state on the boundary. And now, even though holography is very useful, it is still very hard. So we want to use random tensor network to study it. Random tensor network provides natural toy model for holography and reproduces many of the features of holography. And one of them being the Ryu-Takayanagi formula, so holographic entanglement entropy, which is also one feature of holography we'll verify using random tensor network in our talk today. However, to talk about Ryu-Takayanagi formula, we'll first have to talk about black hole entropy, and then we'll lead up to Ryu-Takayanagi. And finally, we'll use random tensor network to see how it reproduces the Ryu-Takayanagi formula. So let us start with the black hole entropy. And a note of convention for our talk is that we'll set the speed of light and Planck's constant to 1. We'll be using the natural unit. Now let us start with the question. So what happens when you pour a cup of tea into a black hole? A while ago, people thought the entropy of the tea will just be gone as the tea goes into the black hole. However, some people did not think so, and Bekenstein being one of them. So in 1972, Bekenstein tried to modify the second law of thermodynamics in the presence of a black hole. And for that, he needed to find a quantity for black hole that will not decrease, because entropy does not decrease. And by then, Hawking proved the area theorem, which states that the area of the black hole event horizon never decreases. So great, combine all these factors, Bekenstein came up with the ansatz that up to an overall factor, the entropy is proportional to area of the event horizon A over Newton's constant G, where Newton's constant is there really just to fix a dimension because dimension of entropy, well, there is no dimension for entropy. As a hindsight, we know that the Bekenstein-Hawking entropy has the factor of 1/4, which is fixed by Hawking during his development of his famous Hawking radiation. And note that this is a very brilliant relation because it relates geometry, just area of the event horizon, to entropy. So for this entropy, this is what we call a coarse grain entropy, which means it's coarse graining over the black hole interior. It's appropriate when we're observing from outside. However, in order to understand more deeply the thermodynamics of black hole interacting with quantum fields, what we want is really a fine grain entropy for the quantum fields. And the natural question to ask here is there a geometrical formula for the fine grain version of black hole entropy? We already have one for the coarse grain entropy, which is here. Do we have one for the fine grain entropy as well? The answer is yes, which is Ryu-Takayanagi. And it is a relation between entropy on the boundary and geometry in the bulk. So imagine if we have a subregion A on the boundary, it will correspond to some subregion A in the bulk, bounded by the minimal surface labeled by gamma A. And the exact shape of this minimal surface will depend on the geometry in the bulk. which you can roughly think about it as if you have a balloon and if you push it into some liquid, the shape of the balloon will change depending on the pressure of the liquid. It's a rough idea. So now what Ryu and Takayanagi did was essentially kind of promoting the black hole entropy to this form, where entropy of the boundary subregion A is given by gamma A, which is the area of the minimal surface here, divided by 4g, where g here is Newton's constant in d dimension. So this is the Ryu-Takayanagi formula, and we will use random tensor network to reproduce this formula. Next, we'll switch gear to talk about random tensor network a little bit. And the random tensor network, maybe an example is maybe this kind of diagram, this kind of graph, where we have vertices and we have connected links and we have some dangling legs, something like this. And the tensor network describes the state of the quantum many-body system as a result of entanglement and correlations within the system. It can also be used to describe mapping from bulk state to boundary state, which makes itself already some kind of holographic code. Let's consider how to set it up, set up a random tensor network physically. Consider some machine that produces entangled pairs. So we have two entangled pairs, and consider some more of those machines and assign some people at some sites. Now, David here will be mapped to the triangle of our tensor network, and the rest three people will be mapped to the three edges extended from the triangle. And now for the diagram on the left, if David does nothing, then the state of the system is simply the tensor product of three entangled pairs, where everyone else is only entangled to David at this point. So Alice is entangled to David, so it's everyone else. Now, suppose David makes a complete measurement with an outcome VA, which is a pure state. Now, David is out of the story since he got a pure state. The rest of the people, Alice, Bob, Charlie, they're now entangled with each other. The posterior state after measurement is given by this expression, and it can be represented by the tensor network on the right. Next, let's do a very quick, simple calculation. Consider a single tensor with two legs, each encoded with a Hilbert space of distinct dimension, namely dA and dB. We would like to calculate the second Renyi entropy on leg A, which in random tensor network coincides with the fine-grained entropy of this subsystem, which is what we want, the fine-grained entropy. So it will have this kind of expression, but what we really want to calculate, just know, is this thing called Z1. And if you trust me, this calculation, as long as it's supposed to some magic for the time being, the result is just 1 over dA plus 1 over dB, roughly. And if we plot it, we'll have this plot. And the solid line here is the 1 over dA plus 1 over dB. And the dots here are the randomly sampled values, numerical values. And we see that it fits pretty well. And for those of you who recognize this, this is the page curve. So this is a small, good. And let us now generalize this to a slightly more complicated network. Let's just take our triangle from previous slides as an example. What we do is we rewrite and represent our fine-grained entropy of a subregion A. Let's call this one subregion A on the boundary. And then we'll assign each vertex with an Eisenspin +1 or -1, so up or down. Let's assign this 2 as up and assign this one as down. Then we can write our Z1 to have this form. And depending on your background, you might recognize this as generating function or partition function. Now the assignment of the spin on the right here is just one specific configuration. And we will sum over all the spin configurations here. The rest of the detail of this equation is, I would say again, magic for now, but I will invite you to observe this equation closely. Among all the terms being summed over, the one with minimum A will dominate, and the other ones will be exponentially suppressed. That spin configuration gives a large A. Now, let's consider in a large D limit, which is all the legs have very large dimensions, so they're roughly essentially the same. The entropy now is dominated by the minimum energy term, which is the one we said just now, the minimum A. And the entropy will have this form. And let's take this as an example. Let's say the sigma in this equation is a cut. It's a line we draw across the links which has anti-parallel spins on the two ends. And A is our boundary subregion. The absolute value of sigma is the number of links we will draw across. We show this quick example here. Just consider this graph with this specific spin configuration. Left sides all have spin up and right side all have spin down. This link is the only one with anti-parallel spins on two ends. And suppose these two are our boundary subregion A, then our sigma union A will be this region here. And because we only cut through one link, the absolute value of sigma is just 1. And if this is the minimum energy given the subregion A on the boundary, then the second reigning entropy, fine-grained entropy, is just log D. So finally, let us compare the large D limit in random tensor network and Ryu-Takayanagi formula from holography. In the random tensor network, we have this equation, which can be massaged into this form, where L is a constant, log D is also a constant, gamma A has something similar to an area. And from Ryu-Takayanagi, we had this. So you see that gamma AC from this formula has correspond to gamma A in Ryu-Takayanagi, and L to the 1 minus D times log D is correspond to 1 over 4G in the Ryu-Takayanagi formula. And also L to the 1 minus D log D, it's just a constant. So it's much like the Newton's constant, serves as the similarity. And that concludes our verification of Ryu-Takayanagi formula using random tensor network. Good. And to conclude, we start with black hole entropy, which is a coarse-grained entropy relation with geometry. And then we said we want a fine-grained entropy. And then we talk about Ryu-Takayanagi formula, and we used a random tensor network, give it a little bit of development, and we verified Ryu-Takayanagi formula in random tensor network. Finally, I would like to acknowledge, I would like to thank Professor Shidong and Sean McBride for mentoring me through this project, and Professor Marv and Professor Z for introducing me to this direction and to theory in general, and Professor Shrednicki allowing me to organize this symposium so everyone here can present. And I would like to thank Dr. B for being my great advisor, and also my girlfriend Hong Ying and my 2 cats for my mental support. And thank you. Any questions?
Thank you. Questions? Kian Lee?
Yeah, so this is more of general question. So from my understanding is like tensor network is usually applied for what, like the amount of entropy or entanglement scale with the area law. So this is one of the reasons why it should work very well in this setup, right? For this black hole problem.
Yeah.
Thank you.
Sophia had a hand raised.
Is there a limit on the size of the system that can be modeled using this random tensor network? Because it seems to deal with discrete particles being entangled and everything. So like in the limit of like material, including many entangled systems on the scale of Avogadro's number, it seems that this might be very expensive.
Yeah, I would agree with that. But I think what we do, let's see, I think on some larger scales, probably maybe we won't be trying to numerically verify it. It will just have some overall behavior. And can be probably well approximated using some good large D limit, like something, some approximation like the large D limit we did just now.
Okay, thank you.
But yeah, I think numerically it will be very expensive to do it. And yeah, if we take large tensor at each vertex, it will be very slow and Mathematica will go mad.
Let's see, David Grabowski, hand raised.
Hi, wonderful talk. I appreciate the use of my name in explaining the entanglement stuff. I'm new to random tensor networks, so I was wondering if you could use this stuff to calculate other ReNUs besides just the second one. I'm not really sure where in your presentation the replica number 2 came in and how you can eventually take it back to 1.
Yeah, that's a great question. In fact, in random tensor network, all the higher ranges are the same. So second range is, if you do the calculation for the higher range, it's just the second range. And also they are also von Neumann entropy, which is a fine grained entropy. So they're just all the same, which is really fun.
That's cool.
Yeah.
So you immediately calculate the von Neumann entropy for free?
Yeah. So that's why we calculate the second range, because it's probably one of the easiest to calculate and one of the easiest to numerically verify.
Okay, great, thank you.
All right, thank you. That concludes the morning session.
The first morning
And
session.
the first morning session, yes, thank you. Concludes the first morning session. Thanks to all our speakers, and we will now have a 10-minute break and then reconvene